So now that we have seen a definition of a distance between distributions, namely we define this total variation distance, which is a good measure for distance between two distributions, we return to a question of measuring the amount of randomness in a random variable. So we'll start with the first question, which studies how many uniform bits can be extracted, perfectly uniform random bits can be extracted out of a given random variable. In fact, we'll relax our requirement a little bit. Instead of asking for exactly uniform random bits or exactly uniform random variable, what we will ask for is approximately uniform random variable, so almost random bits. So here is the formal version. Given a sample x, so given a single observation x from a distribution P, we want to generate a uniform random variable u out of x by applying some function to x. So here is a formal version of this question. So you choose your accuracy epsilon. This is something between 0 and 1, and you can just imagine something large like 0.99 or something like that. The question is, what is the largest value of L such that we can find a function f which takes input x and produces L bits and satisfies this bound. Now what is this bound? What is this bound here? This bound says that the output of the function fx is approximately uniform on L bits. Okay, so it's just like a random L bit string. And when I say approximately, this approximation is in distribution. The total variation distance between fx and u is at most epsilon. Okay, so it's approximately uniform. That's the requirement. What is the largest such L that we can generate? So you may be a bit worried about this error and how it will play, how it will affect your quality of your the randomness that you have generated. So remember that this total variation distance can be expressed as sup over all A, the difference between probability of this first random variable and the second, first PMF and the second PMF. Now suppose you have designed some algorithm which uses randomness generated by PU. What that formula says is that if you replace PU with this PFX, if you replace U with this FX, then all your errors will increase by at most epsilon. Okay, so it's not a big loss if you replace U with fx, and that is why it makes sense to seek random number generation in this approximate sense. So you don't want perfectly uniform, you want almost uniform. Okay, suppose this is the question you want to solve. What will you do? Here is a very simple scheme. I'm putting scheme in quotes because it's not really a scheme, it's only the idea for a scheme. We will divide x into parts with roughly equal probability. Okay, and this roughly equal probability is important here. You may not be able to divide x into parts with exactly equal probability. So roughly equal probability. And this epsilon basically will account for this roughly part. So probability of each part may not be the same as other. And this mismatch between probabilities is what contributes to this epsilon. Also, the more parts you have, the larger is this L. Okay, so you want to divide x into as large number of parts as possible, such that each part has roughly the same probability under P. And if you can do that, then you can generate this f. Then you can find this f with very large L. Keep in mind, this is some small point, but perhaps it's good to revise it here. You can view a function of x as simply a partition. Okay, where each part corresponds to those x for which you declare a particular output. Okay, that's just what you can view a function of fs. Alright, so how do we do this? Let's do this a little bit more formally. So formally, first observation is that we cannot partition all of x into these kind of parts. We at least need some handle over how small the probability of how large the probability of each part is. For instance, if x has just two parts with if x has just two elements with probability 3/4 and 1/4, then there's nothing you can do about it. The only partition you can create is keep one element with 3/4 in one part and the second element with 1/4 in second part. and there is no way you can make this random variable uniform with very high accuracy epsilon. So it is important to first take into account what is the largest probability of an element in X. In particular, we can work with this set, this sort of typical set T lambda. Lambda is a parameter that I'll bring in soon. It is a set of all those elements X such that the probability of X is less than equal to 2 to the power minus lambda. Okay, this is those elements which don't have very large probability. As a convention, we, instead of writing it this way, we will write it in some different form. We'll write it as log to the base 2 1 by px is greater than equal to lambda. So these are elements which have sufficient entropy in them. This is just an informal use of the word entropy. Okay, sufficient randomness in them, sufficiently rare elements. So the sufficiently rare elements are what contribute to randomness. Okay, so suppose you have this set T. We will only work with this particular set T. We will ignore the elements outside it. And what we do is we make a partition of T lambda. So T lambda, we divide it into parts, x1, x2, blah blah blah, xm. We divide it into m parts, okay, and also retain all the other remaining guys in the last part. I'll tell you what these parts must satisfy, m plus 1. Okay. What is this notation? This notation denotes union of disjoint part. So I'm calling it a partition because we assume that x1 to x2, x1, x2, xm, xm plus 1 are all disjoint, and their union is exactly equal to T lambda. So you can, this is our assumption. Okay, it's empty. The intersection is empty. So such a thing is called a partition of this set. So we have this set T lambda, and we divided this T lambda into different parts. Okay, so yeah, so all these parts are your different xi's. Okay, so these parts are your different xi's. That's what we have done. What do we want out of these parts? What we want out of these parts are two properties. So here are these two properties that we want out of each of these parts. First, we want that the probability of all the parts are roughly equal. In particular, we want it to be between 2 to the power minus lambda n and 2 to the power minus lambda into n plus 1. For some n, this n is something we'll bring out later. Why can we do this? Maybe you can think about this question. Pause the video and think about this question. Why can we divide T lambda into such part? Well, the reason is that each element, so this can be done since each element x in T lambda has probability has p of x less than equal to 2 to the power minus lambda. So there is each element is 2 to the power minus lambda. So what you can just do is keep on adding one part at a time until you cross this threshold, and look for the first time you cross this threshold. Since each element has probability at most 2 to the power minus lambda, you will be able to find one set where this will just cross a threshold and will not cross it by more than 2 to the power minus lambda extra. And that's when you stop and take these elements as the first part and now collect more elements for the second part, and you keep on doing this until you cannot cross this threshold, and that's what the remaining elements are, the last part. Okay, so first you take m parts and then you have the last part. Okay, so how many such parts m can you generate? This is an important question. So so this is our assumption. Each part has at least this much mass. How many such parts can we generate? So it is important to note that the total probability of all the things is at most 1. Okay. Therefore, all these parts, so think of this big box representing a total probability. It has this mass of 1. and we are adding these parts in it, x1, x2. Each of them has probability at most this much, and it will add at most to 1, xm. Okay. How many such parts can we add? Well, the total sum here must be at least m times 2 to the power minus lambda and minus lambda into n, right? So maybe I should use a different color for this. So once again, yeah, this is our box of mass 1, and we are filling it with these parts, x1, x2, blah blah blah, xm. And all these parts, the total mass of these parts is at least 2 to the power minus lambda times n times m, and this must be less than equal to 1, because total probability that you can add up is 1, and they're all disjoint, so this just adds. So this means m must be less than equal to 2 to the power lambda by n. That's the best you can do. But on the other hand, since each of them is at least at most this much, then how many parts can we collect? What is the largest number of parts we can collect? Well, we'll collect as many parts as as needed to fill up the probability of lambda, t lambda. Okay, because these parts are all inside t lambda, and each has probability less than equal to each has probability greater than equal to this. Okay. So how many such parts can we collect? So the sum of these probabilities must exceed the probability of t lambda. Sum of all these probabilities must exceed probability of t lambda. But each part has probability less than this. So total sum is m times this, and this must exceed this. So what is the total number of parts you get? The total number of parts you get is this by this. Okay, so you can show that you can find these many parts. Okay. This is some. By the way, this presentation in this lecture may just appear as like a switch in gear. We suddenly are into something very technical. But once again, our goal is to provide a motivation for entropy as a measure of randomness, as a measure of uncertainty, and we'll show, since randomness in a random variable is related to uncertainty of a random variable, we have formulated that problem. That's the goal. But it looks a bit tedious, but it's all very elementary. I suggest that you go back and try to recreate these arguments, think from scratch. These are simple arguments, but require some thought. Okay, so this is the claim, that you can form at least these many parts for a given n and lambda. Okay, so what is your scheme now? Here is my scheme. What I do is that, let me call this number m prime. This is the number of the size of my output domain, this guy. Okay, so what I do is, if x is in this part I, for some I, then I declare that I. Okay, and if, yeah, so note that m is less than equal to the power lambda by n. Therefore, m plus 1 is less than equal to ceil of this. Okay, is less than equal to this plus 1. Okay, that's something we'll use. So when you fall in this ith part, you declare I. If you fall outside this set T, so these parts together form the set T, then you declare an error, or you call it something else. I'm calling it bot for an error symbol. That's my function f. Now the claim is the output distribution of this function f is very close to the uniform distribution. Well, yeah, indeed, all the parts had roughly the same probability. These two upper and lower bounds are roughly the same, so they're almost equal probability parts. Okay, so let's analyze the total variation distance between the distribution of fx and a uniform random variable on m prime. All right, so here is that distribution. So we divide that total variation distance formula into different parts. Look at symbols between 1 and m. What is the probability of each of this symbol? Well, under fx, that probability is pfx of m. We'll evaluate that. Minus 1 by m prime. All probabilities are 1 by m prime under uniform. Then look at this part from m plus 1 to m prime. Okay, this is the probability of those parts. Uniform guys go here. The symbol bot doesn't appear under uniform distribution. So this part is the last contribution, just the probability of bot. So suppose, so this is an assumption here for this part. Suppose probability of T lambda is greater than equal to 1 minus epsilon. Suppose you can find such a T lambda, such that its probability is greater than equal to 1 minus epsilon. Then the probability of bot is the probability that you're outside T lambda, which is at most epsilon. Okay, problem. So this last term we have handled. Now let's look at this green term here. Okay, so for the green term, what we notice is that the probability under f of m plus 1, okay, is at most 2 to the power minus lambda by n. And probability under f of anything more than m plus 1 is 0, because that's the maximum f declares. So this is the bound on this. Now let's look at the uniform distribution. Probability of m plus 1 under uniform distribution or any other element under uniform distribution is 1 by m prime, which is 2 to the power minus lambda by n. So this probability is always smaller than this probability. Okay. So what is the bound? So this is equal to 1 by m prime minus this if you take the mod. And so you get m prime minus m by m prime minus this probability. And m prime by m, this is 1 minus m prime minus some probability. So we ignore this part. So this is less than equal to this. And yeah, actually this is, there is a small correction here. This probability is not T lambda. You only add up to T lambda, probability of T lambda minus the probability of the last element. Okay, this last element can have 2 to the power minus n probability. So this probability is at most probability T lambda minus 2 to the power minus lambda times. Okay, that's the probability of total contribution. So you can show that you must have m at least this much. Okay. All right. So what has happened here? So this last part is the bound for the probability of fx of m plus 1. Sorry, this last part is the lower bound for m that we have derived in this condition here. Okay, so m is at least this much. We just substitute that part. So you get this. Okay. You should repeat this calculations. The way this course is being done is that every calculation is elementary, but you should repeat them. So let's now focus on the last remaining part. So we have already handled this this part, the purple part. Then the green part also we have handled here. And let's focus on the last remaining part. It can be handled similarly. So this is the total contribution for the first m parts into total variation distance. This first part here, this you can verify that the probability that fx takes the value m is just the probability of this set xm, and you have to add over all these parts. And from our condition, remember that m prime is set to 2 to the power lambda by n, and therefore from our condition on this balance part, this is where we are using that fact about balance part. This difference is at most 2 to the power minus lambda. That's how we constructed these balance partitions. So this is 2 to the power minus lambda times m, and m was set to be again 2 to the power lambda by n. So this is at most 1 by n. Okay, so that's this last part. So if you combine all these bounds, this last part is 1 by n. This part is epsilon, and this part is 1 minus this quantity here, and you can check that when you combine these bounds, this is what you obtain as an upper bound for the total variation distance. So the random variable that you have generated is this distance between that and uniform distribution is this much. So when n is large, that's why we wanted this parameter n, this is small. And when lambda is large, again this is small. That's why we have these two parameters. Okay, you set them large to make this distance small. So we set n to be 1 by epsilon minus 1. Okay, and when you set that, you get this bound. So that's the final resulting bound that we get. All right. So what have we shown? We have shown the following result. what we have shown now is so we have shown this theorem. We did the proof first, but that's the theorem we have. Let's focus on this theorem. This looks very much like our source coding theorem. So take any lambda, this is a parameter. Take any epsilon, this is another parameter. Suppose, so this is an assumption. Suppose that you can find a lambda such that with large probability exceeding 1 minus epsilon, this minus log px is greater than lambda. We had seen similar conditions in the source coding, the compression problem earlier. So suppose this condition holds. This condition is something about the underlying distribution P, that you are able to find such a lambda for which this lower bound holds with large probability. Then for the uniform distribution over roughly lambda minus log 1 by epsilon bits. Okay, that's the uniform distribution. We have the total variation distance between this f of x that we designed and pu to be less than equal to some 5 by 2 epsilon plus 2 into 2 to the power minus lambda. This 2 to the power minus gamma. This gamma is set to lambda minus log 1 by epsilon. Okay, that's what we get. In particular, if you set lambda to be greater than 2 to the power 2 log 1 by epsilon, we can set it here. You can set that lambda. Then this becomes log 1 by epsilon. So 2 to the power minus gamma is another epsilon, 2 epsilon. So we get this to be smaller than 7 by 2 epsilon. So you can make it smaller than 7 by 2 epsilon and you can generate these many bits, lambda minus log 1 by epsilon bits. So you can extract lambda minus log 1 by epsilon, almost random bits out of a random variable x, which are, they're almost random because they're within a distance epsilon or 7 by 2 epsilon. So in this course, in general also in practice, when we are analyzing algorithms, it is okay to ignore some such constants in probability of error. That's not so big. The order is important. So you should imagine epsilon to be 10 to the power minus 6, and then there's a small constant which we can ignore. Okay. So we can generate lambda minus log 1 by epsilon bits at distance epsilon. And what is lambda? Well, lambda is the one which satisfies this condition. Okay, so this is the result. This is what we have shown. This looks very much like the compression result, which we saw in the previous week, and which we used to bring in entropy. So can you now stare at this condition and see the role of entropy? So the question is, what is the largest lambda we can have such that this condition is satisfied? What is the largest lambda we can have? And here is the answer, if you didn't guess it already. It's roughly the entropy. You can use Chebyshev inequality to show that with large probability, minus log px is more than entropy minus some correction term. So if you use Chebyshev, you get 1 by epsilon correction. There are sharper inequalities which will give you log 1 by epsilon correction also, but we can ignore this correction term for now. Here is the main term that we should focus on. Okay, and this is a Shannon entropy. How did Shannon entropy come in? That's the expected value of this guy. So with the right choice of lambda here, what is the estimate for minus log px? This is the expected value of this guy. All right. So what we have shown is that you can extract roughly as many random bits as the entropy of the random variable. So this is another different interpretation of entropy as a measure of randomness. Last week we showed interpretation of entropy as a measure of how much you can compress a random variable. What we have seen in this lecture is interpretation of entropy as a measure of randomness. How did we define randomness in a random variable? Well, we define it as the largest number of almost uniform bits that can be extracted from a random variable. So in the next lecture, what we will see is a slightly different notion of measure of randomness. We will define randomness as the largest number of the minimum number of uniform bits required to generate the random variable. Slightly different notion of randomness, and we'll again get entropy as answer. This is the magic of this fundamental notion of entropy. It comes as answer to many related questions. So see you in the next video.